Yeah, so as you can see, I took the introduction to 3 slides very seriously. I don't even have an introduction slide. But basically, yeah, so I'll be talking about today how causal inference can be used to improve and extend a previous diabetes project done by Wolfram Research and in collaboration with Black Country ICB. All right. So first I'm going to talk about the project and motivate it a bit. All right, so there's been a recent push by NHS England to go from a treatment-based model to a prevention-based model for diseases such as diabetes, for those that you can prevent. And so it would be very helpful if we can find insights that can help target interventions towards diabetes prevention. All right? And so because of that, in collaboration with Black Country ICB, we set out to use data from the census and various national level surveys. And the data, it covers variables from diverse categories. For example, you have all of them here, right? Education and skills, exercise, employment, so on and so forth. All right? So from that, we would like to use a large-scale regression analysis to sort of predict what are good drivers of diabetes prevalence in the population. All right? So next. All right. And yeah, so from the large-scale regression analysis, okay, here's kind of what we found. Can you guys roughly see the words on the diagram? Can I zoom in? Oh, I can zoom in. All right, amazing. Yeah. So basically, here's roughly how the results kind of look like. All right. So what we found is that we've done. Here we show the correlations of variables with diabetes prevalence in the population. For example, here you have physically inactive adults correlated with diabetes prevalence with a correlation of negative 0.7577, and here's positive 0.7577 and negative 0.77. All right, and so from that we can then just take the most correlated variables to be potential causes of diabetes prevalence in the population, right? But as you can see from this branch here, let me zoom in a bit. Yeah, these features. Yeah, these features themselves, they also are highly correlated. As you can see, right, you have stuff like Okay, you also have stuff like, epilepsy prevalence being correlated with obesity prevalence and so on. So as you can see, the features, all these variables, they themselves are quite highly correlated. All right. So because of that, as people who've done IV, which I'm sure as most of the audience here would know, that when you try to use correlated features to do estimation of causal effects using regression methods, you're going to get biasness. And so because of that, we've even set out to do pairwise features to predict diabetes prevalence from that. And we've done 800,000 pairwise tests on using that as features to predict diabetes prevalence. But since we have access to the data and we don't have a good hypothesis on how, for example, variables such as people with no qualifications relate with epilepsy prevalence, right? Since you don't have prior hypothesis on how they are related, so we think that causal discovery is a good next step to extend the project to find an idea on how the structure behind these variables, right? So the challenge here is that scalability issues, right? Since you're working with over 1,000 variables, and also the very heterogeneous nature of the sensor data that we're using, which is a mix of both categorical and temporal kind of data that we are working with. So yeah, so those are the challenges that we are looking to solve. All right, and so now let's assume we've done the causal discovery and we got the output of causal relationships. From that, we then want to use that to identify interventions to target known causes of diabetes, for example, age and diet. All right, and this could perhaps be done by causal effect estimation methods to identify the best interventions in terms of the causal effect on long-term diabetes prevalence. And the identified intervention should be realistic and actionable, meaning that you can't change on aspects of the population which you can't change, for example, age, ethnicity, and all that. And for example, a good intervention would be stuff like increasing access to mental health support services and all that. All right. So to sort of extend the project, we are currently working with UCL to secure grants, and one grant we are looking at is the CHAI, the Causal AI in Healthcare grant. Right. And if you guys have any more leads, feel free to talk to me later. And so yeah, so the ultimate goal of this project is to be able to provide an interactive tool for the NHS to guide the making of diabetes prevention policies. And for example, here's an interactive display of the regression analysis results we did, overlaid on a map of Black Country. Yeah, so maybe something interactive along those lines. And yeah, I think that's it for me. Yeah, thank you. All right.
One. Okay.
Thank you. Very interesting. This prediction of diabetes, I guess people have worked on that for a long time. I would guess that there are many possible other forms of evidence that could be integrated into the work you're doing. I just wonder if you had any comments on that.
Okay, yeah. So, because currently, right, the work, the existing work, right, is based on census with a bit of like, national survey, populational national surveys baked in, like, stuff like LSOAs and all that kind of stuff baked in. So yeah, so another potential approach would be to, as you mentioned, like fold in like additional sources of data, right? But the trouble with that is that we find out that some of the sources, for example, we looked at Acorn, right? It's kind of like a data bank that we use. Also, we attempted to use. That's a bit hard to use because there's a lot of redundancy in the data involved. So there's a big part that has to be clean and all that kind of stuff to be able to fold that in. But yeah, that's something we're also looking at as part of the extension that we do for this grant application. Yeah, thank you.
Maybe I have a question.
Yeah. I think in that case, it would be like feature selection first to like deal with the scalability issues, right? Because like I think we kind of do that partially already with this categorization, right? Because for example, if you look at stuff like exercise and all that, it's actually a category of like variables here, right? Adults are physically active. It's kind of like a percentage in the LSOA, how many adults are physically active and all that. So yeah, so it's we kind of do that already, right? So maybe that's also like something we can do, like a nested approach of like a two-level causal discovery approach that could also be something to look at, right? But yeah, so but for now I'm just staying general and say that if you want to do it like without like any feature selection, it could be quite hard with scalability issues. Yeah.
Yeah, thanks. Just a quick question. Doesn't it matter where on the causal pathway all those highly correlated variables are? Because I think it sounded to me, and I'm sorry if I missed this, that you were treating obesity the same as physical inactivity, but physical inactivity is the one that is more likely to cause the obesity. And so you would want to be treating them differently in your model.
Okay, yeah, exactly. Yeah. So yeah, you're right, because of course, right, there's some sort of like background information you can use, right? For example, as you mentioned, like stuff like physical activity. They're going to like lie on different parts of your causal path, right? So at the moment we haven't looked into that because at the moment we are doing like a large-scale ED like exploratory approach. So here we are kind of treating all of them quite like symmetrically, so to speak. But yeah, that's something definitely to fold in like background knowledge on like how these variables like sit on the path and sort of like find a way to aggregate that into a coherent like causal representation of the causal relationships. Yeah, that's something that is part that we are trying to do. Yeah. All right.